Okay, so welcome everybody, and let me open this day officially from the part of the Wigner Research Center. And first thing to say is that I'm very happy to host this event, and I thank the organizers for keeping on organizing this event, which is a good occasion to assemble people, mainly physicists, but not only physicists, who are heavily interested in this large-scale computing. So this is, I think, a very good activity within the institute. So that early this year, beginning of this year, the Wigner Research Center had to define the focus area of research in which we feel we are the strongest and we want to develop further. And 5 such subfields have been defined. The order is not relevant here, but the first one is quantum optics and photonics-based quantum technologies. This was one of them. Then the second is fundamental interactions, new experimental technologies. Third one is structural study of new materials at the atomic scale. Fourth one is artificial intelligence, deep learning, and big data. And the fifth one is somewhat smaller, but there are a lot of researches here which are related to environment protection, things like this. So you can see that 2 of those subfields or focus area are connected to this GPU day. So directly connected is the 4th one, which is related to computation. But also the second one, which, as we learned from the previous introduction, the study of fundamental interactions is the field of physics which demands this high capacity of computation. And now it seems that the first line is quantum optics, quantum technology joins also this demand, or also this participation in the field of computation. So just a brief to set the scheme. So as you see, the horizontal line represents somehow that the physics, the various scales, so starting from up to the largest scale, the largest large-scale structure of universe. So the Wigner Research Center has activities all over this line. And so the very end, right hand represents gravitational wave research, for example. Interestingly, the Institute of Particle Physics, which is one part of the research center, represents the 2 extremes. The smallest other institute, the solid-state physics research and optics, is more in the middle, somehow under the scale, which is closer to us, to the everyday life. So this is the atoms and the bulk material. Now you have to realize that quantum physics is something different. It's not on this line. It opens a new dimension to physics, because here it's not the object which is interesting, but the dynamics, the laws of motion, which changes and which takes place at all scale. So now there are also speculations that at the large scale, the matter at large scale, so the galactical scale, has manifestations of quantum effects. Now, of course, we start from somewhere from the middle to the life, where we can realize quantum effects connected to solid-state physics systems or atomic systems, ions or quantum dots. But this is a different dimension which gives rise to completely new concepts. And such a concept is quantum information. Quantum information is a generalization of classical information in the sense that it has a basic unit, which is the bit, that is generalized to be a quantum. So rather than having 2 states, which is denoted by 0 and 1, now these 2 states of a bit is of 1 these are 2 quantum states which can be in a superposition state. So this is the only addition, but this opens a completely new paradigm. And then this field of quantum information expands to the area of application where we normally encounter the concept of information classically. So there are quantum communication and quantum computing. So in both cases, we have a completely new area of research. So quantum physics at Wigner started long ago. Initially, this community featured only a few researchers, so 1 or 2 researchers and then students. So when we arrived at 2000 or somewhat later, a few years later, quantum physics research was conducted in 3-4 theoretical groups. A big change 2017 when national excellence, in the frame of a national excellence program, the Wigner could embark on a new endeavor, namely experimental activity has been started here. So now, at the moment, now there are 3 experimental groups on top of the 3-4 theory groups that run research in quantum physics. And now we enter again a new time, which is National Laboratory for Quantum Information has been formed, and the Wigner is the leader of this consortial F4. What is this National Laboratory for Quantum Information? So let us define it in terms of the 3 strategic goals. So this gives a good picture of this initiative. So one, that we would like to create a quantum communication network in Hungary. So in fact, there will be a node at the Wigner Research Center, and one where these will be connected. So we can communicate quantum between these 2 partners. And the strategic impact of this, that we are going to be develop this capacity or ability, expertise to join a large-scale network. So there are projects under the European Union to create a European quantum internet, and Hungary will be able to join that network. The second is that we would like to develop not a big country to be able to build a quantum computer, but we can aim at special quantum components which allow for quantum information processing, and we have to develop and maintain the necessary laboratory infrastructure and know-how to do that. And the third one is the quantum computation theory, and this is a very exciting field because there will be quantum as large international infrastructures where one can have a remote access, but we need the background here. We need a group of experts that can compile on that computers, that can compile physics or whatever problems to run them on a quantum computer. A body of experts who knows what are the kind of problems that can be solved. So who are able to develop algorithms. So this is an important pillar of this expertise, or to form this expertise in the country. Okay, so just a few words about quantum experiments at Wigner. Here I highlighted 2. There is an optically detected magnetic resonance. So this is the same device that you can find in medical diagnosis, so magnetic resonance investigation. The big difference that here you detected a single spin. You detect the signature, the single spin, nuclear spin. So this is why it is quantum. So it's a high spatial resolution. ODMR spectrometer is running now at the institute, and nitrogen vacancy centers in diamond are investigated. The other one is, this is called a nitrogen vacancy center in a piece of nanocrystal. It's called an artificial atom because you have an ordered environment, that defect, but this defect is actually like complementary of something that you have an empty space and there is an atom. So it's called an artificial atom, and we are running experiments also with real atoms in an experimental setup that is referred to as the atom-photon interface. It's a cavity quantum electrodynamic system, and actually this is the laboratory activity I'm involved in. So scientific interest is here. But one can say in general, though here I project the quantum states of a rubidium atom, but one can say in general that these quantum systems, whether artificial atoms or atoms, have well-defined discrete states, quantum states. Any two of them can be selected as a 0 and 1 of a quantum bit. And this is a laboratory for us. So you can imagine a small atom as a whole laboratory with a very rich life inside. So we have that can be operated or that can be driven at microwave frequency. We have optical transitions that we can address by lasers, and also the further means that we can apply to manipulate an object which you cannot keep in your hand. Is magnetic field, so we can use the Zeeman effect to manipulate these states. So this is the whole word. And the aim of quantum manipulation is to perform transitions, realize states, measure states in a controlled way. And then we can use these pieces as Lego blocks to build something complicated. So this is the elementary block of a quantum engine. And our aim specifically is to be able to perform all these manipulations, to have a perfect control on atoms. So for example, there is a protocol how one can convert a photon into an atomic state or an atomic state into a photon. This is just an illustration of such a scheme that with a time-dependent pulse, one can extract a photon and a single photon from an atom on demand. So it's a single photon source. With the reverse process, one can realize a complete communication toolbox between photons and atoms. And this is our goal as well. This is why we call our experiment atom-photon interface. So we can generate quantum bits, where the quantum bits are represented in this case, the polarization of photons. And then this quantum bit, the photon, which is a so-called carrier quantum bit because it is used to and then this quantum bit encoded in the photon can be read out in another cavity QED system, so which is the quantum memory. So this gives you a flavor about this experimental development or the objectives. So now we have to realize physically those procedures, those processes which are trivial in the classical world, in the quantum world, to copy the state of one bit to another one, because we have to keep quantum coherence. Okay, so as I said, quantum memory is, for example, the interaction of two quantum bits, when we are talking about two photons, is very big. So photons do not interact. This is why they are good for long distance carriers, but they are not good to perform gates because photons don't interact. But if we copy the state of a photon on an atom, then that quantum information computing, which takes place typically in the microwave regime, and quantum communication, which uses infrared photons. So if you want to connect these two in a quantum coherent way, you need an object that is resonant with both, and an atom is like this. So our other long-term goal is to build an interface between microwave and optical radiation. So these are the exciting process. A lot of work devoted to it, which is waiting for us. And for today, I wish you a good workshop and good platform to communicate. So thank you for your attention.
Thank you very much, Peter, and for this nice introduction. We have a couple of minutes for questions, if any, from, let me ask first from outside. No one from outside, inside. Okay, maybe I have a question in relation to, so what is the, let's say, the short range and the long range of this project, what was formed? So, I mean, I think you have a kind of work plan for the future. So what is the time scale of this activity?
So the National Laboratory has a program for 4 years. So the goals and objectives are defined to 4 years, and these strategic goals that I mentioned are included, so we have to reach them in 4 years. Concerning our experimental activity, in 4 years, we have the ambition to build, so we already have an experiment which is running close to the quantum, to break now this threshold to go into the quantum level. So that's, and this we can achieve in 4 years.
Okay, so then I wish you excellent, successful 4 years. Okay, any other questions? Okay, so then let's thank Peter, and maybe